The fundamental theorem of algebra says that every polynomial f of x has a complex solution to f of x equal to 0. We can find this by just factoring this one. We can factor by grouping. If we take out a x squared, we get x plus 3. And take out a negative 1, giving us x plus 3. And now you can see we can take out an x plus 3. And we're left with x squared minus 1. And so right here we can see that this does in fact have a solution when x equals negative 3. And negative 3 is technically a complex solution where you have negative 3 plus 0i. So we have found a complex solution to this, and the fundamental theorem of algebra tells us that. Now we factor this out, and what remains in this red box, this is again a polynomial, and we know that it has, by the fundamental theorem of algebra, a complex 0. So we can reapply the fundamental theorem of algebra. We can factor that thing down into x minus 1, x plus 1, which is a difference of two squares. And we can see we have further x equal to plus or minus 1 as solutions. These are, of course, plus or minus 1 plus 0i. So that gives us two more complex solutions. So by doing this, reapplying the fundamental theorem of algebra, we get what's called the linear factorization theorem. The linear factorization theorem says a polynomial of nth degree has n complex linear factors in the form of x minus c. So for this polynomial, which is an nth degree polynomial, it can be rewritten as, it's going to be a to the n times x minus c1, just some first complex number, x minus c2, some second one, multiplying all the way up to x minus c n. There's going to be n of them. And they're not going to be necessarily unique. You have to count multiplicities in addition to the actual unique degrees. But if you count all of them together, you will always get the degree of the polynomial. Since factors in polynomials play a similar role as prime numbers do for numbers, we generally like to find these whenever possible. So how do we do this? Well, there's a few techniques that we know. If the degree of the polynomial is small enough, then factoring strategies work. So the strategies that you can use, of course, is like the AC method. We have the quadratic formula. Factoring by grouping, which I showed previously here. And I mean any one of the like x squared minus 4, or like difference of two squares, difference of two cubes, sum and differences of two cubes and squares. Any strategy that we have for that you can use, but only if it's small enough degree. So if it's a large degree, so this is for a small degree. For a large degree, we have to simplify, large degree. We have to simplify it down first. And the way we can do that is we can find the zeros. Of course, how do we do that? That's the first question. And then divide them out. That reduces the degree of the polynomial when we divide out a 0. Finding the zeros, this can be a lot of different strategies. There's some more archaic strategies that they normally teach in this class, but in general, you can just look at a graph of the polynomial and you can find them directly on the graph. Okay, when we have two polynomials that are dividing, right? We've got a cubic polynomial here and then just a linear polynomial there. If we're dividing them out, we can actually use the process of long division. It's done the exact same way. It may not look the same, but it's pretty much the exact same process. So write the first polynomial underneath the division bar, and then write the divider on the outside. And now we're going to ask the question, what is 6x cubed divided by 3x squared? We're always dividing out the first terms and the first term of the divisor. So 6x cubed, 6x cubed divided by 3x. 6 divided by 3 is 2. X cubed divided by x is x squared. That gives us 2x squared. Then we're going to take this number and distribute it into the divisor. So that gives us 2x squared times 3x is 6x cubed. And 2x squared times 4 is 8x squared. This thing we're going to subtract from the polynomial above. I don't have to worry about these terms because none of them are like terms with what we just have. I'm only concerned myself with these first two terms because these are like terms. What this does is it gives us 6x cubed minus 6x cubed is 0. Then 17x squared minus 8x squared. Make sure you're always distributing this negative into here. I write it this way so you can always check your work. If you write it this way, it's going to be pretty easy to see if you make a sign error. But 17x squared minus 8x squared, 17 minus 8, that's just going to be 9x squared. I can bring down the next term and then redo the whole process. So I'm going to take 20, again, the first term here, 9x squared, and then 3x. So we go 9x squared divided by 3x. That gives us 3x. All right, now I can write, let's see, plus 3x. Take this number and distribute it into the divisor. This is actually the exact same thing you would do with the regular problem. So like if I did 7 divided by, I'll do a smaller one, 5 divided by 654. Let's do 684. 5 can go into 6 once, then you go 1 times 5 is 5, then you write 5 there, and you subtract. That gives us 1, bring down the next one, 18. 5 can go into 18 3 times, 3 times 5 is 15, subtract, giving us 3. Bring down the next term. 5 can go into 34, I don't know, 6 times. 6 times 5 is 30. We get 4 as a remainder. It's the same process. So we have 3x times 3x gives us 9x squared. Of course, we're subtracting this. And 3x times 4 is 12x. So subtracting this gives us 0 for the first term. You should always expect 0 as that first column subtraction. And then 27x minus 12x gives us 15x. Okay, let's bring down the next one. 15x divided by 3x gives us 5. So that's the number up there. Distribute the 5 into the divisor. 5 times 3x is 15x. 5 times 4 is 20. We are subtracting them. And of course, you see we get 0 as a remainder. So that means in our original problem here, just clean this up a little bit. We get 2x squared, I don't need parentheses, plus 3x plus 5. It evenly divides out the polynomial. And now you can see that we've gone from a cubic polynomial in the beginning, right? This is all cubic polynomial here. And it became a quadratic polynomial. So it lowered the degree by 1. Here's another division of polynomial function. And we're trying to divide this fourth power polynomial by this squared polynomial. And same process, x to the fourth divided by x squared is always the first step. This, of course, is just x squared. And then distribute the x squared into the divisor. So x squared times x squared is x to the fourth. X squared times x is x cubed. X squared times negative 2 is negative 2x squared. And we subtract, giving us 0 2x squared minus x, 2x cubed minus x cubed is x cubed. And then negative 4 plus 2 is negative 2x squared. Bring on the next term. Divide again. X cubed divided by x squared is x. And multiply it in. X times x squared is x cubed. X times x is x squared. And x times negative 2 is negative 2x. And subtract. 0. We get negative 3x squared. They're both negative now. And that's going to be negative 7 minus negative 2x. So it's going to be plus 2x, so negative 5x. Bring down the next term. We have negative 3x squared divided by x squared, giving us negative 3. Multiply it in. Negative 3 times x squared is negative 3x squared. Negative 3 times x, negative 3x. And negative 3 times negative 2 is positive 6. Subtract. Gives us 0. Negative 5x plus 3x is going to be negative 2x. And then negative 6 minus 6 is negative 12. There's nothing else to bring down, so we can stop there. And this tells us that we have x squared plus x minus 3. Just the answer is there. And then plus, we have the remainder, which is negative 2x minus 12, divided by the divisor, which is x squared plus x minus 2. So this is what the final answer would look like if you have a remainder. You have the polynomial that's actually being divided by, that's being divided evenly. That's what goes in this first spot. And then this, you're doing red here, the red box goes up there. And the blue, which is the divisor, that just goes in the denominator. You always do that. This tells you what's the whole part and what's the fractional part. Now for this polynomial division, we have a polynomial that doesn't have every single power of x. And to do the division properly, it's probably going to be best to write them in. And so there is an x cubed in this. It's just 0 times x cubed. That's how you can write it in and prevent any errors. You don't need to do that, but in general, it's just easier to follow along the process, like keep going along with the process by adding them in. So first off, 4x to the 4th power divided by x is 4x cubed. Multiplying it through gives us 4x to the 4th. 4x cubed times negative 4 is negative 16x cubed. And subtract. It gives us just a positive 16x cubed. Bring on the next term and continue. 16x cubed divided by x is 16x squared. 16x squared times x is 16x cubed. Times negative 4 is going to be negative 64x squared. And we are subtracting. Gives us 0 for these first terms, of course, and then that gives us a plus 64, giving us 60x squared, a positive. Bring on the next term, divide, and multiply it through. Minus 240x, then subtract. That gives us 0 and plus 246x. The final one, we don't actually have to write the 0, but just to keep the process, 246 divided by x is 246, and we multiply it through. 246 times negative 4, do that on a calculator, negative 4 times 246 gives us negative 984. Subtracting it gives us positive 984 for a remainder. And our answer is going to be 4x cubed plus 16x squared plus 60x plus 246 plus the remainder, which was 984, over the divisor, which is x minus 4. Now, there is another way of doing this, And the long division of polynomials takes a while, especially if you have a very long polynomial on top. We can use a different strategy called synthetic division, but only if the denominator is in this linear factor term. If it's anything besides this term, like x plus or minus some number, if it's anything else, then you cannot use the synthetic division form. It doesn't work. For this, I'm going to write it like this. I'm going to write a little box and write the number that gives us the 0. So x minus 4, 4 minus 4 gives us 0. So I'm going to write 4 in here. That's the number that goes in there. Then what I'm going to write next to it are the coefficients of the polynomial. So this polynomial is 4x to the 4th plus 0x cubed plus, negative 4x squared plus 6x plus 0. I'm adding in all of the missing powers. I'm just going to write the numbers in front, though, the coefficients. So 4, 0, negative 4, 6, and 0. I'm going to draw a little bar here. And this is the process that you do. Bring this up just slightly. All right, we're going to go, first off, we're going to go straight down. We're going to add going down. 4 plus 0, there's nothing there, so we're going to write 4. Then we multiply going across. Let me do it in red. Add going down, then we're going to multiply by this number going across. 4 times 4 is 16. Add going down, 16 plus 0 is 16. Then I'll do add going down, multiplying by going up. 16 times, again, 4. You always multiply by that number in that box. 16 times 4 is 64. Add going down, that gives us 60. Negative 4 plus 64 is 60. Multiply going up. I keep forgetting to write the red. Multiplying going up. 4 times 60 is 240. Add going down, we get 240 plus 6 is 246. And finally, multiplying going up gives us 984. I believe that's correct. Yep. Add going down gives us 984. And what we get, this last number is our remainder. And what you can do is you can count up from going right to left here. So this is going to be x to the 0 power, x to the 1, x to the 2, x to the 3, and you're going to keep, you're going to keep going up however many numbers are there. And that means this answer is going to be 4x cubed, because the 4 goes on the x cubed. 16 goes on the x squared. It's a positive 16, so positive 16x squared, and positive 60x, and then positive 246, with the remainder over the divisor, which is still given in the original problem. And that is the exact same answer that we had here. It's the same answer to both of these problems, but synthetic division is much faster. Also, synthetic division has to have this very special form of the divisor, this x minus 4 here, but in general it's going to be x minus c. But this x minus c, this is the kind of factors that every polynomial can be broken down into by the linear factorization theorem. So if you can find these factors, you can use synthetic division to divide them out, thus giving you, we went from a 4th power polynomial to a 3rd power polynomial. We just keep dividing out the factors, and that will give us all of the zeros of the polynomial, and it'll allow us to reduce them down until we can use regular factoring or the AC method or quadratic formula or whatever. What I have here is a 5th degree polynomial. So by the linear factorization theorem, we know that this has 5 zeros in it. And we want to find those 5 zeros. We actually want to find the zeros for this thing. So how do we do that? Well, we don't have any strategies of factoring a 5th degree polynomial. In fact, it's been proven that you cannot have a quadratic formula for a 5th degree polynomial. You can't find one. So we have to use other strategies. And what I have here is the graph of it. If I graph it, I can use this graph to find some zeros that I do have. Now we know -4 is a 0 because it shows it on the graph there. 2 is a 0. And 5 is a 0. We also know that there's no more that are shown on this graph because it's x to the fifth. The end behavior of a fifth degree polynomial is going to go down on the left-hand side as it shows here, and then up on the right-hand side as it shows there. It can have at most 4 inflection points, n minus 1, so this is fifth degree polynomial. 5 minus 1 is 4. We have an inflection point right there. This is kind of like an inflection point, and this is there. There's not going to be anything else. You can zoom out as much as you want, and you won't see anything else there. This is all we have. But we have been given, or we have found 3 zeros. So let's try dividing these zeros out and seeing what we get that remains. Okay, so here I have the polynomial that I have written out, that I graphed, and these are the zeros that we found: -4, 2, and 5. And what I can do is I can think of these things as x plus 4, x minus 2, and x minus 5. These are the factors of this polynomial that correspond to these 3 zeros. And these are in the correct form for us to use synthetic division. So let's go ahead and try that out. We have just the coefficients. We have 1x to the fifth minus 7x to the fourth minus 1x cubed plus 97x squared minus 250x, and then plus 200. So let me get a little space there. Okay, these are the coefficients. Let's go ahead and do synthetic division here. You always add going straight down, right? I'll just write the add going down, and then you multiply going up. Trying to write these in a way that's saves some time there. So add going straight down, there's nothing there written in the first spot, so we just write a 1. Then 1 times -4 is -4. Add going down gives us -11. -11 times -4 is positive 44. Add going down will be 44 minus 1. And multiplying going across. Let's actually use a calculator here. 43 times -4 is -172. Add going down gives us -75. Multiplying going up, that's going to be 150, so 300. Be positive. Add going down, -50. And -4 times -50 is, this is positive 50, not -50. And that's going to give us -200. And that gives us 0, which you need to expect 0. If the number you're testing is a 0 of the polynomial, it should give you 0 in the end, because there should be no remainder. It should always divide evenly the polynomial that you have. What's nice about synthetic division is that we don't have to redraw anything. We've divided out this thing. Now we have a fourth power, right? This is x to the 0, x to the 1, x to the 2, x to the 3, x to the fourth. We don't have to worry about rewriting it, because the way synthetic division works is that we can just divide out by the next number, which is going to be 2 in this case. So once again, we're going to go add going straight down. Oops, let me draw this a little straighter. Add going straight down and multiply going diagonally up. So we get 1. 1 times 2 is 2. -9. -9 times 2 is -18. Add going down, that's going to give us 23, so 25. Yep. That gives us not negative, it's going to be positive 50. It's going to give us -25 when we add going down. And -25 times 2 is -50. And once again, we get 0. You should always expect 0 when you divide them by a factor. And this is a cubic polynomial. we still don't have any really good strategies besides factoring by grouping. If you were to test factoring by grouping on this, it wouldn't work. Let's try dividing out the fifth, the x equal to 5, 0. So same process, add going down, multiply going up, add going down, multiply going up, add going down, and finally multiplying going up, giving us 0. And at this point, we do know how to factor this. This is x to the 0, x to the 1. This is a quadratic equation. So we have x squared minus 4x plus 5. And to factor this, we can use the AC method. A times c is 5, b is negative 4. Two numbers that multiply to give 5, add to give 4. That'd be 1 and 5. 1 plus 5 is 6. Negative 1 and negative 5. Negative 1 plus negative 5 is negative 6. There are no numbers that do that. So we must use the quadratic formula. Okay? Quadratic formula is going to be negative b plus or minus the square root b squared minus 4ac all over twice a. B is negative 4. I'll simplify this. Negative 4 is positive 4. B squared is negative 4 squared, so 16. Minus 4 times a times c. 4 times a is 4 times 1, so 4 times 5 is 20. A is 1, so 2 times a is 2. 4 plus or minus the square root of negative 4 over 2. This comes on the outside as an I, and the square root of 4 is 2. So we get 4 plus or minus 2i over 2. And we can divide out 2 from both 4 and 2, so that gives us 2 plus or minus I. And that's the reason why we could not see them on the graph, is they were complex. And the thing that I graphed was on the real number plane. So we have 5 zeros here. We have x plus 4, x minus 2, x minus 5. Then we have x minus 2 plus I, and x minus 2 minus I. Just make sure that's what we actually found there. Yeah, 2 plus or minus I. And you have to have it in the form of x minus c. That's what the factors look like. So that's why we get x minus 2 plus I and x minus 2 minus I. So that's the factored form of this polynomial. It's a bit odd with the complex numbers there, but this does in fact give us 5 factors, and the linear factorization theorem said there would be 5 factors because it was a 5th degree polynomial. Okay, let's say we have this polynomial function and we know that -1 is a root. So what we can do is we can ask what's the polynomial that we get after we remove -1, and can we find the zeros from that? So of course you could graph this thing. Sometimes graphing doesn't necessarily tell you anything, but oops, it's just the coefficients I need to write, not the numbers. I wanted to try doing synthetic division first and seeing what we get as a result. A lot of times, if you can just divide out what you have and then go from there, it'll give you the next step forward. So add going down, multiplying going up. 4 minus 1 is 3. Multiplied gives us -3. Then -16 multiplied by -1 gives us +16, -48, and we do in fact get 0. So -1 is a root. And here we see that we have a cubic, right? This is x to the 0, x to the 1, x to the 2, x to the 3. You always start with x to the 0, and then you count up from there, if that's not clear. The reason why I wanted to show this is because we have x cubed plus 3x squared minus 16x minus 48. This is a cubic polynomial, and we can try factoring by grouping. It will actually work in this case. I can take out an x squared from the first two terms. From the next two, I can take out a -16, giving us x plus 3. No, plus. This is supposed to be 3 over here. That's the problem. X plus 3. And we can divide out the x plus 3, giving us x plus 3 times x squared minus 16. That, of course, is a difference of two squares, giving us x plus 4 and x minus 4. And we already knew that x minus 1 was also a 0, so we have x plus 1. Now we actually have all four zeros there. So we should expect -1, -3, -4, and 4. Let's graph it and check. Okay, here I have the polynomial and I have the four zeros we just found. They're plotted down here and labeled. So now let me plot the function and see if it actually crosses at those 4 points. And you can see it does. This is the graph that we have, and it directly crosses at each one of those 4 points. And those are going to be all of the x-intercepts that we can find, because the degree is 4, and we know that by the linear factorization theorem, there can only be 4 zeros in this polynomial. And we found all 4. As one final note for synthetic division, it's kind of an interesting property, is that it actually will solve for when you plug in a value. So for instance, f of 3 here, we're just going to plug 3 in here and calculate what that gives us. So just plugging in 3 for x and then seeing what that has. 3 cubed is 27. 3 squared is 9. 5 times 3 is 15, minus 6. 7 times 9 is 63. 15 minus 6 is just going to be 9. And adding those together, we get 27 minus 63 plus 9 gives us -27. Now, what I'm going to do instead is I'm going to use synthetic division on this and use 3 as the divisor. So we have 1, -7, 5, and -6. Add going down, multiply going up. -4. This gives us -12. 5 minus 12 is -7. 3 times -7 is -21. And add going down gives us -27. And -27 is the value that we found for f of 3.